In this problem, we have a car that's moving around a track like this, and they give us the radius, and they also give us the centripetal acceleration of 3 meters per second squared. It says at the instant when the car's velocity is directed due east. So when the car is here, it's going north. When it's here, it's going west. When it's here, it's going south. So when it's at the top, it's going to the east. And this lets us know that it's traveling in a clockwise circle. So it says when viewed from above, the car is moving, so we know it's clockwise, but then we also have to know the speed. So we can do that with AC equals V squared over R. We have the 3 meters per second squared and the 300 meter radius, and that gives us a velocity of 30 meters per second. So the answer is A. In this question, we have a pendulum that's swinging from one side to the other. And the questions are, what are the acceleration vectors due to the ball to positions Q and R? So at Q, we have a force of tension up and a force of gravity down and a net force up to make it centripetally accelerate. So the acceleration is up. When it's at position R, there is no tension because the velocity is zero, so the force of gravity is the only force acting on it, and that acts down, so the acceleration is down, so it's up, and at R, it's down. In this one, it says we have a mass m on a curved point as it moves from point X to point Y, and it says which diagram is a possible combinations of the net force and the velocity and the acceleration. So we know that net forces make things accelerate in the direction of the net force. So F and A must be in the same direction. So we can look through here and see which ones have F and A in the same direction. And there's only two, and it's B and D. And we also know that the velocity must be tangent to the curve, so that gives us choice D. Number 4 and 5. So in this one, we have a spring that's been stretched out that makes this object spin in a circle. So the spring constant is 100 newtons per meter, and it gets stretched 0.03 meters. So we can do F equals kx to find the force of the spring, and the force of the spring is the centripetal force. That's the net force. And the work done on the disc as it's by the spring during one full circle, the force is perpendicular to the displacement, so no work is done. In this one, we have a little dancer that's moving around in this path here. The speed's constant, and they want to know what the graph looks like for acceleration. Well, from P to Q, if it's a constant speed that's in a straight line, there's no acceleration. As it goes from Q to R, it's changing direction, and it's at a constant speed, so it's constantly accelerating. Again, no acceleration here, and then acceleration around the curve from S to P. So from P to Q, nothing. From Q to R, constant acceleration, centripetal, then 0 on the straightaway, then constant acceleration at the end. In this one, a student is holding on to a string, and there's a ball on the end of the string, and they're swinging it around at a constant speed. The question is how much work is done by the ball. Again, the force is perpendicular to the displacement, and work is equal to F dot X, the force parallel to the displacement, so no work is done.